Good afternoon, everyone. Welcome to today's seminar, Why Schematic-Correct Designs Fail at Advanced Nodes. This webinar will start at 2 o'clock, so in the meantime, make yourself a cup of coffee, cup of tea, glass of water, make yourself comfortable, and we will start at 2 o'clock. Good afternoon. Welcome to today's webinar. We will be starting in approximately 2 minutes. So if you've just joined, please get yourself a cool drink, perhaps, or a cup of tea. Make yourself comfortable, and we will start in 2 minutes. Good afternoon, everyone, and welcome. Thank you for joining us today for our webinar, Why Schematic-Correct Designs Fail at Advanced Nodes and Post-Layout Reality in Specialty I/O Verification. My name is Pete Davey from EDA Solutions. I'll be your host for today's session. I would like to start with a very warm welcome to both presenters. Today is a joint webinar created in partnership with one of EDA Solutions customers called Sofics from Belgium. To all of our guests, we appreciate you taking time out of your day to join us. We have attendees from both across the semiconductor industry and across Europe, and we're delighted to have you with us. Before we begin, I've just got a few housekeeping items. This webinar is being recorded, and the recording will be made available after the event. We expect it to be ready probably by Monday next week, and we'll share details with you at that time. Now, to ensure the best audio quality, participant microphones have been muted, but we encourage you to submit questions throughout the session using the chat panel. We'll collect them as we go and address as many as possible during the question and answer session at the end of the presentation. Lastly, for best viewing experience, I'd recommend setting your webinar window to full size, to full screen. Now, if this is your first interaction with EDA Solutions, let me briefly introduce who we are. EDA Solutions is a Siemens EDA specialist distribution and technical partner for Europe, and we focus on the custom IC design community. We help semiconductor companies of all sizes access advanced EDA technologies supported with in-house technical expertise, our commercial flexibility, and close collaboration with Siemens. Now, today's webinar reflects that approach by bringing together experts with deep experience in specialty I/O design, verification, and sign-off at advanced nodes. Many design teams encounter the challenges that we'll discuss today, and a design can appear correct at the schematic level, yet behave very differently once layout effects and parasitics and real-world process considerations are introduced. Now, for specialty I/O structures, where reliability, ESD robustness, and performance must all be maintained, these effects can be particularly significant. So to explore this topic, we're joined by experts from EDA Solutions and one of our customers, Sofics. Sofics provides specialty I/O and ESD IP to enhance IC robustness and performance and reliability across both standard and advanced semiconductor processes. For EDA Solutions, we've got Khalid Teama to introduce key aspects of the custom IC design platform from Siemens. And then Khalid will be joined by our special guest. So welcome Rani Batans, I hope I've pronounced your last name correctly, who is an analog designer at Sofics. She's got extensive experience in specialty I/O design, ESD protection, and most critically, really, silicon-proven implementation strategies. Their presentations will examine the gap between schematic intent and post-layout reality and explain the mechanisms behind these issues and demonstrate practical approaches to achieving greater confidence in verification and sign-off. So with that, Khalid, I'd like to invite you to the stage so that I can hand over control of the presentation to you.
Hello. Hi there, Pete.
So Khalid, nice to see you. It's all yours.
Thank you very much. Thank you very much for the intro, Pete. My name is Khalid Teama, and I'm the Technical Support Manager at EDA Solutions, and I will talk to you today about the Siemens Custom IC design flow from the product perspective. So first off, the Siemens ecosystem is actually surrounded or is actually targeted towards providing an answer for every challenge in the IC design industry. Our ecosystem includes tools that tackle challenges in custom IC design, analog and mixed signal verification, physical verification, digital verification, and also digital design side of things. This flow and ecosystem is backed by our foundry enablement team, who establishes formal relationships with foundries and makes sure that the processes you're targeting are working on our tools. Taking a specific look at the custom IC design platform backbone flow, it starts with custom IC SEdit schematic capture tool, which natively works with open access databases. The formal design and test aggregation tool is Solido Design Environment, which works hand in hand with the Solido Simulation Suite. Layout is constructed using LEdit, and IP characterization is done using the Solido Characterization Suite. And finally, your design is verified with Calibre Physical Verification Solutions, which provide a gold standard sign-off verification quality. Our flow is applicable to numerous applications, including analog design, RF, mixed signal, standard cell generation, and memory designs. Today, we will focus on providing an overview of the Calibre Parasitic Extraction solutions and the Solido Simulation Suite and how they can be used to create robust designs backed by evidence from our colleagues at Sofics. So taking a closer look at the Calibre design solutions, Calibre plays a critical role in the physical design and verification stages. It works across multiple design levels, from IC design at the bottom of the hierarchy, through block design, chip design, and increasingly important today, the chiplet design and 3D IC verification. The 3D illustration at the bottom shows how modern semiconductor products integrate multiple technologies from die level through package integration, and Calibre provides verification solutions across this entire stack. So whatever your design complexity or product roadmap is, Calibre provides the comprehensive verification flow you need for successful silicon. Calibre offers highest quality solution in the industry. It delivers excellent verification results while using less memory than other tools. And this is why Calibre is used for 90% of the most complex designs worldwide. Calibre has a long history of success. Our development roadmap always meets customer needs as technology advances, and users appreciate that Calibre is easy to use, reliable, and helps them work more efficiently. One major advantage of Calibre is that it connects with all major design tools and flows. No matter what design environment you use, Calibre integrates smoothly with it. Calibre is a approved sign-off solution at all major foundries. This means that when you verify your design with Calibre, you're using the same tool that foundries use to check if your design can be manufactured correctly. We are making Calibre easier to use in cloud environments, giving you more options for how you run your verification tasks. The Calibre is much more than just DRC and LVS tool. It's a comprehensive verification platform which addresses the full range of today's challenges. Beyond our best-in-class DRC, our physical verification solution includes advanced capabilities like nanometer DRC recon for faster incremental runs, auto waiver to streamline rule exceptions, multi-patterning support for advanced nodes, and yield enhancer to improve manufacturing outcomes. Our circuit verification extends beyond industry-leading LVS with tools like xACT for parasitic extraction. Also, we offer LVS Recon, which brings verification to the early stages of the design flow and gives you a heads up on potential violations before sign-off. Our reliability tools offering, particularly important today, is the Calibre Perk for advanced reliability checks and Insight Analyzer for detailed analysis. Empower for power integrity verification, which is critical for automotive, medical, and other high reliability applications. There's also an emphasis on the shift left principle, which many of our tools support, and it emphasizes on identifying and fixing issues earlier in the design process and significantly reducing costly late state changes. At the center, you can see how Calibre connects the entire ecosystem: foundries, EDA tools, customers, IP providers, and cloud platforms. And this integration is key to the strength of the Calibre platform. Introducing Shift Left. It aims at detecting design problems early in the design process, avoiding costly delays in tape-out dates. This is being introduced in our new products, Calibre LVS Recon and also DRC Recon tools that will be introduced in the Siemens ecosystem flow. Now let's take a look into the parasitic extraction solutions. Extraction reveals the real behavior of your layout. It's not just the ideal schematic. When you draw metal traces, you end up with resistance, which causes voltage drop and delays. When you having metal wires also can introduce capacitances, which means slower switching and power consumption. Parallel routes could introduce coupling capacitance, which can introduce crosstalk and noise. Long wires could introduce inductance, which means ringing and overshoot at high speeds. So this means that the parasitic extraction that Calibre provides is key to verifying the real behavior of your layout and the quality of your layout design. Extraction is not optional. It's your safety net before the expensive tape-out decision. For analog and RF designs, precise matching and symmetry becomes critical, which requires accurate coupling and substrate effect modeling. For digital designs, it means that there are millions of nets and time-critical paths, which needs fast extraction and with selective accuracy. Memory designs have repetitive structures and also bitline coupling, which requires hierarchical extraction for speed. The results of skipping extraction can be catastrophic. The numbers tell us that 60 to 80% of timing violations could be found post-extraction if you don't do this parasitic extraction step. 30 to 50% of power increase due to unmodeled parasitics, and a respin cost that goes up to $5 million depending on node. Looking at the parasitic extraction flow by Calibre, foundries on the left-hand side use xCalibrate to generate their RC rules, which are given to designers in the form of LVS and extraction rules. Designers feed this data along with their layout and source nets into Calibre. The output of the extracted net lists includes the formats shown on the right-hand side. Calibre provides solutions for parasitic extraction in the form of rule-based extraction, XRC, and field solvers, xACT and xACT 3D for the highest accuracy. Parasitic inductance extraction is possible using Calibre XL. Comparing the two methods, the rule-based extraction usually comes with faster runtime. Complete layout could be run over complete layouts over regular devices, and it's not usually a target for characterization. However, field solvers are used for standard cell and memory cell characterization, angled shapes such as MEMS and touchscreens, sensitive RF layouts, and reference for extraction. If you would like to extract values of parasitics less or around 50 attofarads, absolute error. The rule-based XRC is run for nodes 22 nanometers and above. 16 nanometer is normally run, 16 nanometer and below, Calibre xACT is used, and Calibre xACT 3D is used for MEMS, touchscreens, and memory applications. Now let's take a look into the Solido Simulation Suite. The Solido Simulation Suite is an integrated suite of AI-accelerated high-performance simulators that provides accurate verification of all custom IC sign-off flows with comprehensive analysis. So, when you use the Solido Simulation Suite, you are capturing high performance with order of magnitude speedups using these tools and simulators, unified SPICE, fast SPICE, and library IP custom simulation, and these tools are foundry certified by all leading foundries worldwide. It includes these simulators, So the SPICE simulation technologies, they provide a broad coverage across analog RF mixed signal memory, library IP, 3D IC applications. We have the Solido AFS, which is an industry standard SPICE simulation for nanometer AMS, RF, and custom digital designs. As production tested transient RF, noise and aging simulations optimized for advanced processes. Solido SPICE, which is accelerated SPICE simulation for next generation AMS RF memory and 3D IC designs. Lead customers of these tools demonstrate 2 to 30 time verification speed up on large designs compared to competition. The Symphony simulator is an industry standard mixed signal simulation incorporating Solido simulation for analog and Questa for digital co-simulations. Production tested transient co-simulations optimized for mixed signal designs. Solido LibSpice provides accelerated SPICE simulation for batch verification of library IP designs, and it's uniquely constructed for small designs providing 4 to 15 times speed up. Solido SPICE has superior performance over competition. Benchmarking results show twice to 30 times speed up on large pre or post layout circuits across analog memory, RF, and custom digital applications. The graph in front of us shows how Solido SPICE competes in terms of speed against competition. The tools come with a powerful waveform viewer, the Solido Simulation Suite. It ships with the Solido waveform viewer S-Wave. S-Wave provides a powerful post-processing and waveform analysis capabilities for simulation results. It supports both built-in measurement functions and custom user-defined processing scripts. The environment integrates seamlessly with Siemens Custom IC tools, as well as third-party editors and flows. In conclusion, what I would like to say in conclusion is that the Calibre Parasitic Extraction delivers accurate post-layout parasitics, while Solido Simulation Suite transforms them into fast, reliable, silicon-accurate circuit verification. Thank you for listening, and with that, I would like to hand over to Rani.
Thank you, Khalid. Good afternoon, everyone. My name is Rani Batens. I'm an analog design engineer at Sofics. And I will first give a short introduction. Then I will talk about 2 design cases where we found at Sofics issues with the design during the verification of the layout, which we did not expect based on the schematic results. Then in the end, I will talk a bit about a feature of Calibre XRC xACT that I find very useful. And then lastly, a summary of this presentation. So first, as I said, I'm an engineer at Sofics. Sofics stands for Solutions for ICs. We are an IP company based in Aalter, Belgium, and we focus mainly on the chip edge. So this means we design things like overvoltage tolerant GPIOs, low power voltage regulators, ESD protection, and stuff like that. Here you see a representation of our design methodology. So first, and the EDA solution tools we use. So first there is the design phase where we design a schematic in SEdit and verify its performance using the Solido Simulation Suite, more specifically Solido Sim AFS. Then there is the layout phase where we use LEdit, NMLVS, and NMDRC. And lastly, the final verification where we verify the layout performance based on the parasitic extraction with Calibre and then also, again, the simulation suite. So the first design case concerns a GPIO in TSMC 22 nanometers. We designed a GPIO compatible with 3 different supply voltages, 1 volt, 1.2 volt, and 1.8 volt, each with 10% variation. There is an additional 3.3 volt power rail to overdrive the driver. Features of this GPIO are an input and output enable, a pull-up resistor, which can also be disabled, and programmable drive strength. And the circuit includes 2 kV HBM ESD protection and was designed for a speed of 25 megahertz for loads up to 100 picofarads. So what was the issue with the circuits? Based on the schematic, everything was fine. We had good simulation results, overall corners. Everything was within spec, like the pad rise fall time, the pad leakage was within spec, but then we extracted the layout with Calibre and verified its performance, and we saw that in some corners, the GPIO pad does not switch. So for some reason, the signal does not propagate fully through the I/O, and that even though the layout is DRC and LVS clean. So to look into the cause of this issue, we look more into the waveforms. We compared also the schematic netlist to the XRC netlists. But first, through the waveform, we could see that the signal stopped propagating at a level shifter that is shown here. This level shifter consists of 2 input devices that drive a PMOS latch, and it shifts an input signal in the I/O domain to the 3.3 volt domain. As I mentioned earlier, the I/O domain could go as low as 1 volt minus 10%, but the threshold voltage of these input devices ranges from 0.5 to 0.8 volts, depending on the corner. And as you can see, in some corners, then there is very little overdrive over these input devices, which in schematic simulation was not a problem. However, when we compared the schematic netlist to the XRC netlist of this level shifter, we saw that of these input devices, some parameters were different. And it turns out that these parameters increased the threshold voltage of these devices, which causes the latch no longer to switch because the input devices are never turned on, basically. I illustrate the effect of these changing parameters on this slide. So here you see the Solido waveform analyzer, and I simulated the gate source voltage versus the drain current of one of these input NMOS devices. And I did that for both the schematic netlist and the XRC netlist. And as you can see at the end of the graph at 0.9 volts gate source voltage, the schematic device has double the drive strength of the layout device. And this even though, as I said, the layout was LVS clean, so it should be the same device. This is a very big difference, which was caused by this parameter change, as I said, but what is the cause of this parameter change itself, where we had to look a bit further in what these parameters meant in the documentation. And there we found it was due to the well proximity effects. So at the layout, at well edges in the layout, the doping concentration is a bit different. And when your device is located close to this edge, it can influence the device characteristics, like the threshold voltage. In this technology specifically, we had to be careful with the N-well, but also with the OD layer, so the active layer, in this case, the OD2 layer. And the layout shown here is the one I simulated in the previous slide, and the OD layer is there indicated, and it has minimum size, so the device is located very close to the edge. Now, we know what the cause is, so we also know the solution, which is just to increase this box of OD2. That's what I did here on the right. You see it's made much bigger. Device is no longer located that close to the edge. To verify my thoughts here, I extracted the layout again and redid the simulation. And I added the result here in the blue curve. And you see that this result is much closer to what we would expect from the schematic simulation. So now we found a solution. We can solve this in the actual layouts. One way is, as I showed you, increasing the space between the well edge and the sensitive devices, but that's not what we did in the end, because as you see, this consumes a lot of area. So we actually redesigned the level shifter to make it more robust so that it's performed even with the well proximity effect present. And this, in the end, consumed less area. So this was the first design case. The second design case is about a low power voltage regulator in FinFET technology, TSMC 4 nanometers to be more precise. We designed a voltage regulator that generates 0.6 volts and 1.2 volts out of 1.8 volt, and it was designed for the 1.8 volt TSMC GPIO in this technology. Again, the schematic simulation showed everything was fine. The DC leakage current of the circuit was less than 1 microamps. The layout was drawn, extracted, and again, we tested its performance and compared it to the schematic results, as I show here again in the waveform viewer. The good news was that this time the circuit worked. So the output voltages were within spec. It could drive the loads as expected, but the DC current consumption, as you see, is increasing slowly up to more than 20 microamps of current, which is a big increase. So again, we digged further in the waveforms, looked into the netlist, and also looked into the layout itself, and there we found the culprit. The culprit was a PODE device with floating gates. PODE stands for poly-on-OD edge, and in this FinFET technology, it's actually kind of dummy device. But what it really is a regular device with a recognition layer over it, so that it is recognized as this PODE device. And the mistake we made is by placing this in the middle of a real device, and this way it also acted as a real device with a floating gate, as shown in the layout in the middle here. On the right, you see a schematic representation of what happened. So the PODE device is shown in red, and with a floating gate, it decreases the impedance of the path from 1.8 volts to ground, and this increases the leakage. But because this recognition layer was on it, the layout was still LVS clean, because it was not seen as an actual device. The solution to this is either connect these gates so that this parasitic device no longer causes the leakage current, but even better is to use the device as it is intended and only on the OD edge, and for the rest use real dummy gates, as I show in the layout screenshot right here. This screenshot is not of the same voltage regulator, it's of another one we made also in 4 nanometers, but this time a 3.3 volt voltage regulator that generates 4 different output voltages, and it was designed for our own Sofics 3.3 volt overvoltage tolerant GPIO. Overvoltage tolerant, I maybe explain, is in this technology, the I/O devices can only handle 1.2 volts. If you use the overdrive version, they can handle 1.5 volts, and you see the supply 3.3 volts, and also actually the 1.8 of the example I showed you is higher than that. So that makes this an overvoltage tolerant design. That was the second design case. Now I will talk about a feature of Calibre XRC xACT that I find very useful, because as I have mentioned multiple times, the way we find the cause of these layout issues is by looking at the waveforms and looking into the XRC netlist, but these can sometimes be hard to make sense of. but you can ask Calibre to make it easier for you by making it use the net names, the schematic net names in the XRC netlist. For that, you of course need an LVS clean layout. And the feature you need for that is the PAX netlist statement. I show here some screenshots for the Siemens manual. There are multiple options, like layout names is the standard, but I like to use source names, and it makes a netlist much easier to navigate. I will show you an example right here. So these are two netlist statements of the same device, of the same layout, but the top one is extracted with layout names and the bottom one with source names. The corresponding nets are given the same color to make the comparison. And in the top one, you can make some things out, like you can see VSS there because a pin was placed probably. But in the bottom one, you can really see the full hierarchy of the cell where this net is located in. Also for the instance name and for parasitic and R and C, it will be very clear which nets they originate from. And this way it's much easier to navigate, and you actually know what you're looking at in the waveform viewer, or what you can find more easily the exact device in the netlist. So we're almost at the end. I will give you a short summary. Advanced technologies are very layout sensitive, and good simulation results based on schematics are no longer enough. You really need to verify the performance of the layout by extracting the parasitics with Calibre and simulating this netlist, because this catches different issues due to parasitics, dummy devices, and layout effects like the well proximity effects. An important step in finding the cause of these issues and finding the solution to these issues is analyzing the waveforms and the netlists, and specific Calibre settings can make it much easier for you. So that was it. Thank you for listening, and now I will hand you back to Pete.
Brilliant. Thank you very much, Rani. Tell you what, Rani, why don't you stay on the stage, and Khalid, you come on there too, please, so I don't feel so lonely. So brilliant. Everyone out there, thank you very much for listening so far. Please, we've got a number of questions already in the queue, so to speak, but if you've got any other questions or anything you'd like clarifying, please just drop them in the chat window now. So before we step into the Q&A, let me remind you, first of all, I will share a link of this whole recording, probably by about Monday next week, so you can view it on demand or share it with any of your colleagues. We will also share a PDF of the slides directly to the people who've attended. If you would like to know anything more about the products or the approach taken by Sofics discussed today, please visit sofics.com website or edasolutions.com. And of course, we would welcome the opportunity to discuss how we can help you directly. So you can contact Rani on the email address is shown there. You can contact Khalid, or you can contact myself, or you can, I'm sure, go to our respective websites and go through the contact pages there. So what I'll do is I'll pop the email addresses in the chat window so they're convenient for you. And then I'll just turn off the presentation, so it'll leave the three of us on the screen, hopefully. Stop sharing. All right. So I have questions lined up. And if you're both ready, Rani and Khalid, you ready for some tricky questions?
Yes.
Brilliant. Well, the first one goes to you, Rani, and it's from Jean, I think he's in France. Does TSMC N4 technology allow going as high as 3.3 volts?
Yes, it does. Well, it's not easy, as I mentioned. The overdrive devices are only capable of withstanding 1.5 volts. So that means you will need at least a 3-stack. And it's not easy to pull this off, but We are capable of doing that at Sofics. We have a GPIO, 3.3 volt GPIO in this technology, 3.3 volt voltage regulator, and also 3.3 volt ESD protection. So it's not easy. You really have to know what you're doing, but yes, it is possible.
Great. Actually, this is a brilliant question because it's from someone called Peter, who's also in the UK. So Peter, thanks for joining in. And Peter's question to Rani is, and it appeared towards the end of your presentation, which concrete issues did you solve with the source name solution?
Yes, I'll give maybe a more specific example related to the design cases. So, for example, in the voltage regulator design case, when we already had a feeling that the issue might be these PODE devices, because we saw them appearing in the net list here and there. And so when I knew, okay, this is the sub-circuit where the issue is, and this circuit has these PODE devices, I could just basically search for it in the net list, because I knew in what cell it was located and which specific net name I had to look for. And there I just deleted this line, redid the simulation, and I saw that the issue was solved. So there we already knew what the cause was. I hope this is a clear example.
Great. Peter, if you've got any clarification, then please just whack it in the chat window. Khalid, you're up next. So it's kind of a fairly general one, I guess, but there's Thomas from Germany asks, can you talk a bit about Calibre in the cloud solution that you mentioned early on?
Yep, sure. Yeah, of course, there is a great effort in making life easy for everyone, and removing any limits in terms of resources, which is exactly what the cloud provides. Ability to accessibility for your design team, and also virtually unlimited resource. So with this, there's a new product in the market now for Calibre, which is called Calibre Connect or Cloud Connect or Calibre Connect, which allows you to not only use Calibre. You can already install Calibre on the cloud, but also this enables you to use it in a mix of tools. So even if you have a third-party tool, then you could install Calibre on a separate cloud or even on premise, and then that allows you to launch Calibre from your editor tool, and then be able to display the results there. So this is an example of the ongoing effort to support the cloud solutions.
Okay, thank you, Khalid. Another one's popped up from someone called Claire, also in the UK. How does shift left verification reduce project risk and turnaround time?
Well, the discovering issues late in the project time means delaying tape out, means that things are going to be very costly. And there is the recon products for LVS and DRC that come with Calibre. And what they do is, they allow you to detect any issues related to LVS or DRC early on in the design process. So rather than having to wait to do, an extensive, let's say, verification towards tape out and then discovering big issues, that means that you're going to have to delay the tape out. Well, LVS Recon and DRC Recon products resolve this issue by helping you detect these problems early on in the design process.
Great, thanks, Khalid. It's a probably point, because actually I've been working on something internally. We're doing another one of our EDA expert series, and I've got an interview with one of our Calibre product specialists, just talking about this whole topic of shift left. Now that's kind of in the production at the moment, so to speak, but we hope to release that in 2 or 3 weeks' time. So watch out for that. That'll give you a bit more detail on shift left. I'm going to take this next question from Yasser. So Yasser, It's to Rani. Rani, how do you overcome mismatch and process variation in 22 nanometer analog design? And also there's a kind of an extension bit and local global variations.
Yes, well, the designs I usually do, which are the GPIOs and the voltage regulators, there it's really because we have done research into architectures that are robust enough to handle all these problems. So usually we try to make it that by design, it is, yeah, this mismatch, this process variation is no longer an issue. Of course, it starts with designing it for a typical corner, and then you expand to all the other corners. But usually, it's just the architecture that controls it.
Okay, great. Next one, you're going to be the popular one today, I think, Rani. So you're going to be in the hot seat. How did you realize that the problem might have been from PODE?
Well, because we saw that normal dummy devices, they don't really pop up in the netlist in mature technologies, and this one did. And well, it's not in the schematic netlist, so this is quite a big difference. And then, as I mentioned earlier, when I had this suspicion and went to look for this specific PODE device in the netlist, and I just removed it from the netlist and did the simulation again, the problem was magically solved. So then it was quite clear where the issue was located.
Nice, nice. Another question for you from Wilfred, who I think is in Switzerland. You've been talking about XRC on advanced nodes. Shouldn't you be using xACT for these advanced nodes? So I guess that's the Calibre product, xACT.
Yeah, that's correct indeed. Especially for the 4 nanometers, we do use xACT for the advanced nodes. It was just an easy way to talk about it, that I mean the extracted layouts by saying XRC, but we do use xACT.
Great. So thank you very much, everyone, for your questions so far. I've still got about 4 or 5 questions left in the queue. If you do have any questions or thoughts, please don't hesitate to share them with me, and I'll do my best to put them to you. So next question is it's Khalid. You're back in the hot seat. So what types of issues are commonly missed if extraction is skipped before tape out?
Well, skipping extraction before tape out, can miss some parasitic RC effects, coupling noise, IR drop, timing degradation, signal integrity problems, and these issues may only appear in silicon. So, these types, sometimes you have to deploy the right tool, for you to extract the right type of, let's say, group of issues, right? Or, for example, using the right engine, if it's Calibre XRC, xACT, XRC, xACT 3D, sorry, maybe even thinking about using mPower, which is used for IR drop analysis. You could also start thinking of deploying PERC, for reliability side of things and ensuring the reliability of your devices or of your IP, for example. It's not just trusting the layout that you have and trusting the schematic that you have, but also thinking that whether you have the right tool in house, and not just thinking of sometimes even just basic parasitic extraction. If you're doing an RF design, you might want to consider, for example, inductance and extracting parasitic inductance using Calibre XL. So bottom line is, to identify the common issues that are relevant in your design and what that design domain entails. For example, even in automotive applications, reliability is very critical, right? So it's identifying these two things, and then inquiring about the right tools is probably the best approach in this case. And that's why we are here at EDA Solutions, is to discuss with you your design requirements and to talk to you about what you could potentially need for your for your type of application.
Actually, that's quite good. That sort of fits into another question which has come up with customers saying they're using DRC and LVS extensively, and they're kind of saying, they understand why to do extraction post layout simulation, but it's another big investment. Can you say a few more words about why they should make that investment?
Yeah, I mean, DRC and LVS, they would confirm the geometric correctness, and connectivity of your design. They do not validate the real electrical behavior, after these parasitic effects have been introduced. Working at low frequency or high frequency, you have some certain types of parasitics that introduce themselves in the layout. And so simulating the layout after extracting those parasitics to ensure that it meets the performance, your power and noise and timing criteria is very important. So it's of course no longer a DRC and LVS anymore. It's also about simulating your layout to reality, if you will.
Okay, thank you. I'm going to flip back to Rani for a question from Felix in Austria. And talk about working on TSMC 22, and the solution. The MOS on the right was so much smaller than the MOS on the left. I think that was a slide where you had two images on the slide, one which was zoomed out, one which was zoomed in. Can you explain?
Yes, about layout. I think that's just the left one was with the smaller OD layer, and the right one was with the big OD layer. That's why it was zoomed out, because the OD layer was so big. But they are essentially the same device. They were both LVS clean with the same schematic. It's just the right one, the device looked so small because the OD layer was so big.
Okay, I hope that clarifies it for you, for Felix. Fiona from the UK is asking, this is kind of an interesting one. How is data privacy ensured in AI tools? And I guess where that's coming from, the background for the question is in TSMC statement, it's not allowed to use their documents and information in AI tools, not even in internal tools.
Yeah, as that question, is that on the Siemens products, I think, because
it's probably on the
AI
Siemens
products
that
I was showing. Yeah. So on the for this type of, I mean, you're right. I mean, AI is the buzzword these days, isn't it? But of course, many people have the concern of privacy and all the rest of it, and you have every right to think of this. I mean, we have different levels of intelligence deployed in our tools, and sometimes these buzzwords could get mixed up. For example, in Solido design environment, we have language machine learning algorithms, and we have intelligent algorithms working in the simulators. But when we are talking about AI specifically, Siemens offers a flexible deployment options. So of course, the one of the products is Fuse AI. It's still in early stages of introduction, and this is being offered on premise. Because many foundries or many users, of course, are they would like to have this. Most of the people would like to have this data in-house. I believe there's also cloud deployment options, but there's on-premise for sure. So there's deployment flexibility is there. There's what's called the secure RAG, which is which features advanced custom access mapping and controls to ensure that only the authorized data is processed or accessed, and so forth. So there is information available on this on the Siemens website, which I can post in the chat if you like. and they talk more about the security and the deployment of these products in your flow.
Thanks, Khalid. So to everyone, I'm sorry, I thought we were doing so well up until that point. We managed to have a seminar which wasn't going to talk about AI today, but I guess you had to throw it in. So you got a bit there. But we're going to pass back to Rani. Why can't we use TSMC voltage regulator for TSMC I/O? Do you want me to repeat the question? Oh, you're on. Your microphone's muted.
Yeah, I wanted to reduce the background noise, but yeah. No, I understood the question. So this points to, I think, the voltage regulator from the second design case, which we designed for the TSMC GPIO. Well, in this PDK, there wasn't a voltage regulator for this GPIO. So that's why we design our own. And also, usually when it does exist in the PDK, it usually consumes too much power. So we really focus on designing really low power voltage regulators.
Thank you. Okay, I've got two more questions actually. There's one for each of you. So if any of you have got any more questions, now would probably be a good time to type them in, and then we can ask them. If not, then we'll do these two questions and then we'll wrap up. So, this one for Khalid. Khalid, how does Calibre integrate into the mixed signal and 3D IC workflows?
Yeah, so we've got workflows within Calibre platform that support mixed signal, for example, verification, and these integrate the analog and digital, the flows and the parasitic aware flows within a single and unified flow. There's also Calibre 3D Stack, which is a product for inter-die connectivity and verification of connectivity side of things. And of course, in addition to this, there is flows for analog and this type of workflows. So if this type of question, I think, is best answered if you have a conversation with us. Maybe we can take a look at again, like what your design aspirations or your design goals are, and we'd be more than happy to identify the right products in that respect. There's many solutions that are diversified, and they could be deployed in 3D IC workflow, or just a regular mixed signal or regular analog type of design.
Thank you. So we don't have any more questions in the queue beyond this one that I'm going to ask to Rani, so you can have the last word. It's from someone called Ash, I believe they're in Scotland. How big do the XRC net lists become?
Well, in FinFET especially, they can really explode. So if you have a schematic netlist of, say, 1,000 lines, it can quickly go up to hundreds of thousands of lines in FinFET. So if you have to navigate that, it's not easy.
Well, that's great. Thank you. So we've run the audience dry of questions. Before we go, I'd just like to ask either if you've got any last words you'd like to say. So I don't know who would like to go first. Ladies before gentlemen, I think is appropriate. So Rani, would you like to say a few last words?
Yeah, sure. I enjoyed giving this webinar, and thanks everyone for listening and the interesting questions.
Brilliant. And Khalid?
Yeah. So parasitic extraction is not an option. It's mandatory. Use Calibre Parasitic Extraction along with the Solido Simulation Suite. For accurate simulation and modeling of your layouts. And talk to us if you have any questions or concerns, or if you don't know the way, we'll be more than happy to lead you. Thank you.
Great. Well, let me say a big thank you. So a big thank you, first of all, to Sofics and to Rani for all your work preparing for this and doing a great presentation, answering the questions so eloquently today. Thank you very much. Khalid, as always, a pleasure working with you. Thank you very much. To everyone who's attended, thank you for investing your time today. I hope it's been truly valuable to you. If you've got any other questions, then you can hit any one of us with them through email. And our respective companies would be only too happy to help. As I said before, on-demand version will be ready in about a week's time. And also probably 2 or 3 weeks' time, we will have that new EDA expert episode available on our website, which will be talking about shift left in some detail. So with that, thank you very much, everyone. And thank you, Rani. Thank you, Khalid. And it's goodbye from all of us. Bye-bye.
Bye.
Thank you.